So this lecture introduces the method of variations of parameters. It's another method that we can use in order to solve a second order linear ordinary differential equation. So let's consider second order linear differential equations in this form. You have y double prime plus b of t, y prime plus c of ty plus f of t, where all the functions b of t, c of t, and f of t are continuous on an interval I that contains t0, which is the initial point. Well, if we can find the fundamental set of solutions, let's say y1 and y2, be a fundamental set of solutions to the homogeneous part of this equation, then for any choices of t0 in the same interval I, a particular solution's big YT of the driven ordinary differential equations here is given by y1t, which is one of the solutions in the fundamental set of solutions, multiplied by the integral from t0, which is the initial value, to t of negative y2, which is another function in the fundamental set of solutions, multiplied by f of t, f of s, which is the functions here on the right side of this equation, divided by the Kronsky value, Kronsky functions of y1 and y2 in terms of s, ds. And you can pay attention that why we're using s instead of t. So we're using s instead of t because on the integral we integrating these functions right here and using t as the boundaries. So that's why we need to use a placeholder variable, which is usually we call it s. You can call it a, b, c, d, whatever letters that you want to use. Just to it has to be different than t, because when you integrate it, it can be confused with t. Okay, so you use s here. And this is the formula for the particular solutions or specific solutions of this differential equation using y1 and y2, which forms a fundamental set of solutions of the homogeneous part. And pay attention to the formula here. y1 multiplied to the integrals in terms of y2, f, right? And the Kronsky of y1 and y2. Plus y2 multiplied by the integral in terms of y1 times s and divided by the Kronsky of y1 and y2. And one thing that we want to pay attention is in this first part here, you have negative sign. And the second part, you have positive sign. And so once you find this particular solution, you can find the general solution to this differential equations is y, right? The function y equals to c1 y1 plus c2 y2, which is the solution to the homogeneous part, plus this particular solution, big Y of t. All right. And you might wondering, how could we derive this formula? Let's go through a proof. Okay. So again, this is a method of variation of parameter. Remember, in the first order differential equations, we talked about this method. When you found one of the solutions to the equation, you just multiply that solution to a function, right, to find the second solution. In this case, we have two functions that forms a fundamental set of solutions to the homogeneous part. Then in order to find the particular solution here, we want to multiply each of the functions by a function v1. Let's say multiply y1 by v1 and then add y2 by v2. The goal is to find v1 and v2 to find the particular solutions. Okay. So by the assumptions, this is y of t, big Y of t. And once we have big Y of t, we can find the first derivative of y and the second derivative of y. The reason why I want to do that is because we assume that this is the solutions. Then we can plug y, y prime, and y double prime into the original equation and to the dE, right? So that this is y double prime, this is y prime, and this is y, okay? And then you can rearrange, right? I can rearrange all of these terms because I want to factor the V1 because again, I always want to find V1 and V2. So I found all the terms that involved V1. I factor V1 out, right? I factor V2 out. And in this case, I still have B of T as a common factor. And that's it. And then I just rearrange this term in order to notice that for any of the functions V1 and V2 that satisfy V prime 1 Y1 plus V prime 2 Y2 equals to 0. So where do I find this term? I found this terms here. If this terms equals to 0, okay, for all t in the interval I, then for all V1 and V2 that satisfy this, then it follows that V1 prime Y1 prime plus V2 prime Y2 prime has to be equals to f of t. So if this term equals to 0, then this term equals to f of t, because keep in mind that y double prime vty prime cty1 equals to 0 because y1 is a solution. Also, y double prime 2 plus vty prime 2 plus c of t y2 is also equals to 0. So we notice that these two equations here forms a system of equations of the unknown V1 and V2 because we know Y1 and Y2. So we can just figure out V1 and V2. Okay. Again, if this is 0, V1 prime Y1 plus V2 prime Y2 equals to 0, then this terms here has to be equals f of t. And we come up with a system of equations. And then we can transform the system of equation into an augmented matrix. Okay. And then the goal is to solve for V1 and V2. And it's a system of two equations with two variables. We know how to solve for V1 and V2, and we convert this matrix into a matrix equation form, right, to get V1 prime, V2 prime. And with this matrix here, multiply to this matrix to get 0 and f of t. And we can find, so solve this matrix equation to get V1 prime equals to negative y2 times f of t divided by the Kroneskiin of y1, y2. And again, remember the Kroneskiin is y1 times y2 prime minus y1 prime times y2. That's the Kroneskiin. Kroneskiin functions of y1 and y2. And V2 prime equals to y1 times f of t divided by Kroneskiin of y1 and y2. So we found V1 prime and V2 prime in terms of y1 and y2 and f of t. So remember, if we have V1 prime, we can find V1 by integrate both sides. And if you integrate the right side here, you get V1. If you integrate this right side, you get V2. Look, if we have V1 and V2, and if we have some initial values, we just need to integrate this functions from t0, which is the initial value, up to t, up to the value of t, okay? And then because we integrate these functions up to t using t as the boundaries variables, we need to change from t to a placeholder variable, which is, I call this s, right? So you're doing the same thing, you just replace t by s and ds here, okay? Similarly for V2, you integrate these functions in terms of s, and you raise this from, you integrate it from t0, which is the initial value, to t to get V2. And then once you have V1 and V2, you plug it in the formula, right? V1 times y1 plus V2 times y2 will give you the specific solutions big Y of t. And once you have specific solution and you already found the fundamental set of solutions y1 and y2, then you can find the general solution y of t equals to c1 y1 plus c2 y2 plus big Y of t. More specifically, you can replace big Y of t by v1 times this integral and v2 times this integral. So this is a method that helps you find general solutions, also a particular solution to an IVP for some second order linear ordinary differential equation that are in this form. Okay, you have to start with the correct form with all the conditions before you can start using this method. All right, again, this is a method of variation of parameters, and you can see that this is the summaries of how you can use this method. Find y1 and y2 to be the solutions of the homogeneous part. Find big YT, which is the particular solutions using this formula, and we just derived this formula. And you understand how can we know that this is the correct formula for this particular method.